In this unit, we are dealing with vibrating columns of air. And just like on a string where we can have a standing wave, we can have standing waves in columns of air. And that's actually how musical instruments produce pure notes, musical notes. They vibrate or create a resonating column of air that has a standing wave in it. So we create a vibration on one end, and that creates the compressions and rarefactions within our instrument that produces notes for us. Now, an instrument might have one end closed and one end open, or both ends open, but it won't have both ends closed, or we wouldn't get any vibrations out of it. So let's consider the case where we have two open ends. Now, I'm going to talk about things in terms of pressure, but there's also a way to talk about it in terms of displacement. So I'll show you that. And we're talking about the pressure of the particles or the displacement of the particles. To me, it makes sense to think about this in terms of pressure. Some people like the displacement method better. So I'm going to draw a string. So here's my string fixed on both ends, and we know its fundamental wavelength, or fundamental, is 1/2 of a wavelength fits on that string, or we have lambda 1 is equal to twice the length of the string. And that's because both ends of the string are fixed. Both of them are nodes. Okay, well, what about in this open tube here? Well, if we think about this in terms of pressure, this is a fixed pressure at this end, this is a fixed pressure at this end. It's atmospheric pressure, okay, which is going to be like the medium of this. It's not going to be super high pressure, super low pressure. It's going to be atmospheric pressure, but it can't change because it's open to the atmosphere. So I like to think of an open tube as having a node at either end, and then it's just a heck of a lot like a string, and we get the same thing. Lambda 1 is equal to 2L, lambda 2 is equal to L, lambda 3 is equal to 2 over 3L, and we have the same pattern. Lambda n is equal to 2 over n times the length of the tube. Okay? Now, the displacement method of looking at this actually looks at this in a slightly different way. Okay? If we think about this, these ends of this pipe are open, which means these particles of air are free to move this way, free to move that way. Same over here. These particles of air are free to move this way, free to move that way. This particle of air in the middle is trapped in the middle. It can't really go anywhere. So in terms of displacement, we think of this as being a node in the middle and antinodes at the end. And then instead of having the string that looks like a loop of vibrating string, we have this thing that has antinodes at either end. But that didn't change anything. This is still half a wave in this tube, right? We went from a crest to a trough. We went half of a wave. So that doesn't change much. It just makes more sense to me to think about the nodes on either end. Now, the case varies a little bit if we go to a tube that is closed on one end, because if it's closed on one end, we don't have that fixed pressure of atmospheric pressure anymore. Now, this end can actually vibrate quite a bit. We can have high pressure or low pressure. It's not open to the atmosphere, so the atmospheric pressure does not fix this end. So it could have very, very high pressure, or it could have very, very low pressure. This end of the tube, though, is still fixed. So again, let me draw my string. Okay? And I'm going to go ahead and I'm going to draw the fundamental. Okay? The longest wave that would fit in this string is right here, and that's because this end is fixed. But if that end was free to move up and down, then we could actually fit a longer wave in here, because we could make our crest right here and our trough right here. That wave could move, and then that means in the distance from this end to this end, instead of getting half a wave, we're actually getting only 1/4 of a wave, because this would have to come all the way back down and then like that. Well, that's the same thing that's going on here. We have a pressure node on this side, and we have an antinode on this side, and that means our first wavelength, lambda 1, is actually 4 times the length of this tube. We only have 1/4 of a wave in this tube. So a closed tube will produce a longer, lower frequency note than an open tube of the same length. And now the interesting part about this is what happens to our next one. Okay, is there a lambda 2? Is there the next wave? Well, think about this. We only have the option of an antinode on the left side, on the closed side, and a node on the open side, which means those things are always 1/4 of a wavelength different but they can't be a half of a wave different. So if I wanted to, what's the next wave I can put in here? Well, let me redraw my string wave real quick. And I'm going to start with an antinode over here just so it matches that. And so let's see, so I'll have my antinode goes through, reflects, okay. Alright, so there's my wave, and then here's, right, it's a standing wave, so it has these loops that vibrate back and forth. Okay? Now, what are my options? If I start with an antinode and I go to a node, I can have this, which is a quarter of a wave, but I can't go to this next antinode, which would be a half of a wave. That doesn't work because I can't have an antinode on this end. So my next option is actually right here, which if we look at that, that's this whole distance is half a wave, and this is another quarter, so I have 3/4 of my wavelength here, so 3/4 of lambda. And that's where I can get my next standing wave to form, which means I don't really get all the nodes, antinodes like I had before. So we only see the odds, right? We had this one, the first, then we skipped the antinode, and then we're here. So we only have the odds on this one. So just like we had lambda 1, or 1/4 of lambda 1 is equal to the length of the tube. But instead of going now to 2/4, which would give us a half of lambda 2 to equal L, we're not going to have that one because that one doesn't fit. That's half of a wavelength and it doesn't fit on there. So we only get the odds. So this one's gone, and we go to the next one, which we call lambda 3, or 3/4 of the length of the tube, or if you'd like, then we have lambda 3 is equal to 4/3 the length of the tube. So with the open tube, we only get odd harmonics. So we have lambda 1, lambda 3, lambda 5, and the wavelength of that harmonic is given by 4/n times the length of the tube. So lambda n is 4/n times L, but in this case, n is equal to 1, 3, 5. It is not equal to all the integers, it's equal to only the odd integers, because we're always going to have this odd step since the ends are opposite instead of similar.